Today we are now going to discuss significance of fiber and process parameters. We have already learnt about the rotor spinning machines, its working principles and various parts or elements that makes this particular machine. Now, we are going to discuss the importance of fiber parameters. So, first thing is, you see the two diagrams are there on the right hand side, and the diagram shows fineness on one side and the other side Indian brakes, fineness as well as yarn strength. Now, what is the importance of fiber fineness in the case of rotor spinning? First of all, irrespective of the spinning, the number of fibers in the yarn cross section depends on fineness of the fiber for a given count of yarn. When the yarn count is fixed, now how many fibers are there in the cross section of the yarn will be decided by fineness of the fiber. In that case, it is not dependent on which spinning system we use, whether it is ring spinning, rotor spinning or any other spinning, does not matter. The number of fibers in the yarn cross section is dependent only on fineness of the fiber for a given count of the yarn. In the case of rotor spinning, if we have more than 110 fibers, we will have good running conditions. So, you have to see that the fineness of the fiber is chosen in such a way that it should not fall below 110. Otherwise, the running condition of the machine will suffer. 90 to 100 is a transition zone, and less than 90 spinning is going to be problematic in nature. What does it mean problematic? That there will be too many, very frequently we will encounter end breaks, and therefore, we should never allow the number of fibers in the yarn cross section to go below 90 at no cost, because spinning will be almost impossible and the yarn will be too faulty, because too many breaks will be there. This efficiency of the process will go down, it will not be cost effective at all. So, that is, these are the important aspects, and here the fiber fineness is going to play a role. Finer the fiber is easy to spin, because torsion resistance of the fiber bundle is less in comparison to coarser founder bundle. The torsional resistance or torsional rigidity is dependent on the diameter of the fiber. So, finer fiber means their torsional rigidities are less, and therefore, it should be easy to twist. Yarn twist can penetrate the spinning zone and forms very good PTE. PT we have already discussed earlier. PT is peripheral twist extent, that is part of the twisted yarn that remains in contact with the rotor groove, that is called peripheral twist extent. So, we need a certain amount of PTE to ensure stable spinning, otherwise the spinning becomes very unstable. So, finer the fibers, better it is. Now, it is shown in this diagram that as the fiber becomes coarser, the end breaks race goes up, whether it is ring spinning or rotor spinning, in both the cases. Coarser fibers mean less number of fibers in the cross section, cohesion is less, the twist is not in a position to penetrate the fibers which are there in the groove of the rotor, and as a result the end breaks will go up. The other thing is that with the coarseness of the fiber, the strength of the yarn also goes down. There will be loss in cohesion between the fibers. Therefore, fineness plays a very important role. Then comes the fiber strength. Typically, strength translation efficiency in the case of rotor spun yarn is 35 to 50%. That means, whatever the fiber tenacity that we get, 35 to 50% of that tenacity is actually realized in the yarn. So, if the fiber tenacity is x, the yarn tenacity is going to be 0.35 x or maximum up to 0.5 x. So, there is a 50% reduction almost, or even more than that could be in the tenacity translation. However, greater fiber strength can permit to spin at higher speed, and stronger the fiber, stronger is the yarn. That is in generally true both for ring spinning, rotor spinning. If we use strong fiber, then only we will get strong yarn. Strong fibers are less likely to break also, because the action of the opening roller teeth on the fibers is very aggressive and very intense, and because the opening roller runs at very high speed, and the end breakage of the fibers can be avoided if the fibers are strong. Less number of fibers will break. Now, typically the strength of fibers, some fibers are stated here which are used for spinning: cotton 20 to 50 cm per tex, viscose yarn 18 to 35, viscose modal 35 to 45, polyester 25 to 65, acrylic 20 to 35. So, these data are anyway available in other textbook also. So, typically the fibers which are used in the case of rotor spinning are stated here, and their strength and elongation values are also quoted. Next comes the importance of fiber length. So, what we see in the diagram is, as the staple length is going to increase, the yarn strength is going to increase. That is the general behavior. So, short are the fibers, lower is the yarn strength; long are the fibers, more will be going to be the yarn strength. And with increasing staple length, yarn evenness goes down. This is something very different in comparison to ring spinning process. In ring spinning, we do not find it. Longer fibers means always very uniform yarn, but in the case of rotor spinning, this may not be true. Longer fibers means much more uneven yarn. We will see gradually why the yarn becomes uneven when the fibers are long, but still shorter fibers are not really good for rotor spinning also. There has to be some minimum length, and that way long fibers is always good, but too long may be bad. So, medium length fibers are best suited for rotor spinning. Fiber proportions should be as small as possible. Which fibers? Fibers greater than 1.3 dr, where dr is the rotor diameter. These fibers, that means 1.3 times the diameter, whatever fibers are there, they should be as small as possible. And in the case of man-made fiber, this is also true, and for cotton also. For man-made fiber, this should be less than this. For cotton, what it is saying, that these fiber proportions should be as small as possible. That means the very long fibers. for a given diameter of the rotor, the fibers which are 1.3 times more than diameter of the rotor, these numbers should be less. Minimum there, the better it is, because these fibers are prone to form wrapper fibers. We will see that how wrapper fibers are basically produced. I think we have already discussed this earlier, and therefore, very long fibers are not good. For man-made fibers, fiber length should be less than 1.3 dr. Typically, fiber length for 32 to 38 millimeter and fineness between 1 to 1.6 degrees Celsius is most suitable for. Man-made fibers do not have any short fibers, whereas cotton fibers have short fibers. And since man-made fibers are almost, you can say, hardly any short fibers are there, unless we generate short fibers while I am processing the fibers on blow room and card, because carding machines may generate some short fibers because of very intense carding action. Otherwise, man-made fibers will not have any shorter fibers, but typically, therefore, the length of the fibers would be 1.3 times of the diameter, less than that, because most of the fibers, if it exceeds this length, most of the fibers are going to form wrapper fibers. Whereas in the case of cotton, this is not true, because cotton has its own fiber length distributions, and therefore, you have shorter fibers, you have medium length fibers, you also have very long fibers. Too long fibers are, in the case of cottons, are bad. They are going to form the wrappers, and wrapper fibers is something which is a nuisance for rotor spinning, and we want to avoid them. So, too long fibers left to the rotor increases end breakages due to many wrapper fiber formation which weakens the yarn. We will see that when we discuss the structure of the rotor yarn in some other lecture, that the wrapper fibers are a type of fibers which are wrapping the core part of the yarn. So, the rotor spun yarn, we can say that it has a core and it has a sheath kind of thing. The sheath is basically formed by the wrapper fibers. Maybe sometimes part of the wrapper remains within the yarn, the rest of the fiber is actually forming wraps around the core part of the yarn, and these wrapper fibers, more their number, they are going to weaken the yarn, because they do not participate in load bearing when the yarn is actually stretched. So, when the yarn is stretched, how many fibers are supporting the load really matters, and that decides the strength of the yarn. In the case of rotor spinning, because many fibers are simply wrapped over the main core, these fibers will not get tension when you stretch the yarn, and therefore, they do not contribute towards the strength of the yarn. So, they are going to contribute towards the mass of the yarn only, not towards the strength, and hence lesser than number, better it is always. So, we have to see that how to reduce the number of wrapper fibers, which will otherwise spoil the yarn quality. So, we want to avoid them. Fiber selection is based on spinning performance and quality needed for a given end use. Now, here a table which is shown for different spinning system, how the fiber parameters are important. So, for rotor spinning, if we look at it for cotton, strength of the fiber is most important, that is rank 1, followed by rank 2, which is fineness of the fiber. The rank 3 is coming the length of the fiber. That is how it has been shown by some author, that in ring spinning length is most important, in edge spinning length is most important, but whereas in rotor spinning the strength of the fiber becomes most important, and length occupies the third position, because long length does not necessarily mean strong yarn in the case of rotor spinning, because there is every likelihood that these long fibers may be part of the wrappers which will not contribute towards the strength. So, some guidance is given here in the lower table, that is typical length of waste fibers for cotton, short staple and medium staple is given, and these fiber lengths are suitable for spinning count of yarn of 15, 18 and 35, or depending upon the basically the length of fibers. For man-made fibers 30 to 40 mm fiber length can be chosen, and we can go up to 50 NE is very fine count. We can make 36 NE, we can make somewhere in 30s. It is possible to spin with 32 to 40 mm fiber, because in the case of man-made fiber, if you choose a length between 32 or 38 or 40, almost all the fibers will be of same length, there is no short fibers in it. Whereas for cotton, this is not going to be true. So, after discussing the fibers, now we are going to discuss the sliver preparation. First of all, sliver mass variations. For good short and long term evenness, the CV mass CV of the sliver should be 2.5 to 3.4 percentage. Very short term variations are compensated by the back doubling. I think we have also discussed this term back doubling earlier. The very short term variations in the sliver will be compensated because of the back doubling which is happening within the rotor, because fibers are actually accumulating within the rotor in the form of layers after layer, and there is a doubling action because of this, which is going to suppress the very short term variations present in the feed sliver. Short term variations which are 1 to 3 mm deteriorates yarn regularity as they are not compensated. One meter variation in sliver CV can lead to count variation in the yarn, since draft is in the range of 50 to 200. Depending upon the count, we give a draft of 50 to 200 to the sliver to make a yarn. So, 1 meter variation in sliver CV may lead to count variations in the final yarn. So, some typical values are also shown here. For yarn count less than 20, the CV of sliver, CV 1 meter CV of slivers and 5 meter of sliver. These are some kind of norm, you can say, which the industry follows. The other important fact is the trash level in the sliver, especially in the case of cotton. The permissible trash level decreases with reduction in rotor diameter and increases in its speed and increase in its speed. That is, if I go for higher speed, my sliver should be very clean, and if I want to go for a smaller diameter rotor, this sliver has to be very clean. There will be very low trash content in this sliver. And if I want to spin faster using a smaller diameter rotor, we have to go for a sliver which is very clean. That is what becomes important. So, the permissible trash content versus the rotor diameter, there is a kind of graph as is shown is here, that is trash content, the diameter is more, trash content, you can say tolerable trash content in this sliver is going to be higher. For larger rotor diameters can manage with little more dust content in the sliver, or the smaller diameter rotors are very sensitive to the dust content, and hence we need more clean sliver to process them, process on rotor spinning machines. High trash content affects what else? It affects end breakages, it can create Moir effect, it will create nap generations, and it can gradually change the character of the yarn from compact to bulky. If we do not bother much, then we will see that the quality of the yarn is suffering from beginning to the end of the package because of high trash content and its presence in the groove. Whatever trash is left in the sliver, the entire trash cannot be taken out. Some trash will be left in the sliver always, even if we go for combing, still there is some trash particle left, and these trash particles will always go inside the rotor, but from the rotor they have no escape route for them. So, they will be generally staying within the rotor and they will accumulate within the rotor groove, and that becomes a source of problem, especially Moir effect. It can lead to end breakages, nap generation, and gradual change in yarn character because of accumulation of dust in the groove itself. It will affect the flow of twist, and that is why the problems will arise. Next one is draft. How much draft you should keep on the machine? This question always comes, that is, for a given count, what should be the sliver count? Feeding a lighter sliver at a faster speed should be preferred over feeding a heavier sliver at a slow speed, since combing action is more intense with heavier feed. So, if you have a choice, that is finer sliver, high speed, or coarser sliver and slow speed. In these two cases, it is better to go for a lighter sliver and feed them little faster than using a coarser sliver and feeding it slower. That is not preferable. Total draft, sliver count by yarn count, and that varies between 60 to 350 depending upon the count of yarn I am going to produce. Draft distributions, draft in the opening zone is around 500 to 2000, in the transport channel it is 5 to 6, the friction draft on the rotor wall around 1.5 to 2.5, and draft from feed to rotor could be the multiplication of the individual draft Z1, Z2 and Z3. If we multiply these three, we get the total draft in the opening zone. As fibers are recollected in the groove in the form of layers, back doubling occurs, which is how much is back doubling in this case? ZR is pi dRt by 1000. It can be shown or proved that the back doubling that occurs is dependent upon diameter of the rotor and the twist, both of them are responsible. Now, we go to the next slide. So, total draft, if we try to find out, it is the multiplication of Z1, Z2, Z3 by division by ZR. What is ZR? ZR is the back doubling occurs, which is ZR. That means several layers of fibers are again getting sandwiched within the rotor groove. So, that also has to be taken into account. Therefore, total draft is Z1, Z2, Z3 divided by ZR. Now, typically the draft for various yarn counts, the typical values are quoted. These are can be practiced, that is what we see here. If the count becomes finer, the draft becomes high. When the draft is actually coarser, the draft is also low. So, this kind of draft that exists, it could be 70 to it could be 130, 150, it can go up to 250 also. And if that is the draft we use, then we can find out what is the type of sliver that we need to manufacture the rotor yarn. So, total draft range, if somebody asks how much draft is normally used, we can say the range is between 70 to 250. Now, fiber flux and speed profile at different stages. A diagram is shown here, and now I will do some calculation to show it how these figures or a figure close to this are coming. So, this is the different zones: feed roller zone, feed zone, combing roller zone or opening roller zone, air transport channel, rotor groove and actual yarn formations. So, I have 1, 2, 3, 4, 5 different, you can say, sections of the machines, and we want to find out what is the fiber flux. Now, first let us look at this small numerical just to find out what could be the values. Sliver count is 4 kilotex, fiber fineness is 2 decitex. Number of fibers in the sliver cross section, we can find it out, it is going to be 20,000. Then the yarn count is 40 tex. And fibers in the yarn cross section is going to be 40 into 10 by 2. Yarn count is 40 tex. So, this 40 comes here, I make it convert into decitex by multiplying by 10 and then divide by the fiber fineness, which is given in decitex, which is 2, and therefore, the total value is coming 200. Fibers in the yarn cross sections, therefore, is going to be 200. Sliver feed rate is 10 meters per minute. That is, we feed the sliver at a very slow speed, hardly 1 meters per minute. The opening roll diameter is, suppose it is 80 mm and speed is 10,000 rpm. Then opening roller surface speed we can calculate, which is going to be 1759 meters per minute, almost 1800 meters per minute. Draft in transport channel is, we can find it out, 6000 by 1759, that is 3.41. This is the draft within the transport channel, that is, the fibers are leaving the surface of the opening roller and through the transport channel is landing on the rotor wall. So, while traveling the small distance, opening roller surface to the rotor, there is a draft because the air is accelerating continuously, and the draft in the channel could be to the order of 3.41. That is how the drafts are shown, and if you look at this diagram, the speeds are shown at different stages. how the fiber is flowing through the machine and at what speed. That fiber speed we can find out from this diagram. And second thing that we can find out is how many fibers are there in the cross sections. So, that data is also given depending upon the sliver count and the sliver or the yarn count, the sliver count in actual practice, and we can find out these values. The fiber flux in the beginning which is 20,000, it comes down to 2.38, which is very low, and the draft at different stages are also shown here. The combing roller, the opening roller is very high, then it is coming down 3.41, further down to 1.40. So, these are the fiber flux and draft values at during different stages of production. That is what is given here, and the transport channel draft is shown to be 3.41. Its transport channel draft is only because of accelerating air current. So, what is the air velocity at the entry and what is the velocity in the exit? If you know this, take the ratio, that will give you the draft in the transport channel. This gives a flow chart of the rotor spinning process, you can say. So, if the rotor spinning process flow chart is shown here, that we start with short staple fiber or common oil, whatever we get, or also we can take regular cotton, man made and fibers and blends. These are the 3 different types of machines also. So, what we see here, there are various practices in the industry. One is you take the fibers in the short staple form or comb bundle or mix them together, whatever we want, and then the first operation is the blow room operations, where we will further open and clean it, and then from the blow room it can directly go to the auto leveler card and it finishes there. From there I get sliver directly, which we can feed to the rotor spinning machine. This is one options of the process flow chart. The other one is that you from the blow room you feed it to the auto leveler card, and then from there it goes to a drop frame which do not have any auto leveler. So, we give one passage to the drop frame, make this fiber a little bit parallel to each other, and then we feed it to the rotor spinning machine for subsequent spinning operations. This is one process. The other one is normal card we take, we may not take auto leveler card, we pass it through a drop frame, and now we have a second passage drop frame with auto leveler available. So, we can go basically are giving 2 drop frame passages with auto levelers in the drop frame itself. We will get a quite uniform sliver, and this can go for spinning on the rotor spinning machine. That is another process. The other one is card itself has auto leveler. After auto level, cut sliver goes to drop frame, and from drop frame, breaker drop frame, it goes to the finisher drop frame. So, these are, you can write finisher, and this is breaker. So, breaker drop frame and then finisher drop frame. So, breaker drop frame passage and finisher drop frame package. So, finisher drop frame package, that is in finisher drop frame we try to keep the auto leveler will even out the mass variation which is present in the sliver. So, the advantage is there of having auto leveler in the end, because whatever faults are mechanical faults are generated by the card or by the very fast drop frame, all of them will be then even out because of the auto leveler drop frame that we have as the last process. Fiber orientation is going to improve, and at the same time the mass variation is going to be evened out. by having this thing. So, whatever process flow chart that we follow, that depends upon what is the yarn count I am going to make and how good quality yarn I want to produce, which is also dependent upon the buyer's need and his paying capacity. What the buyer need and how much he can pay, depending upon, we have to choose the processing sequence. So, we have one processing sequence, 2, 3, 4, there are 4 processing sequences which have been described here, and as I said, depending upon the quality of the yarn, the count of yarn that the buyer is looking for and the payment he can make, we choose one of them. Now, it is requirement of twist. How much twist is required in the yarn, or how much twist multiplier is required in the yarn? Twist multiplier can vary from 2 to 8, huge range. 2 is for super soft yarn and 8 is for crepe yarn. If the T is the twist per meter, then alpha E indicates here the twist multiplier in English system is TPI by root over NE. Twist factor in Tex system is T into root over Tex by 1000, T by root over Nm, that is also 30.3 the twist multiplier in English system, alpha E. So, alpha indicates twist multiplier and the letter, the subscript indicates the system, the counting system we are using. And alpha metric is T by root over Nm, where T is indicating twist per meter and TPI indicates twist per inch. Alpha m equal to alpha Tex, alpha E is 0.033 alpha m. And here is a table that gives you an idea, typical twist multiplier which is chosen for different types of yarn. For knitting yarn, TM range is 3.2 to 4.5. For PC yarn, that is polyester cotton yarn, it could be 2.7 to 3.7. So, a kind of guideline or suggestion is given, which are generally practiced in the industry, and one can follow this, and we can generally say from this table that for weaving yarn, that the yarns which are meant to be woven, the twist multiplier is on the higher side in comparison to the yarn that is meant for knitting or hosiery, because for weaving we need strong yarns. For hosiery we do not need so much strong yarns, and hence if we keep more twist, we expect the yarn to be stronger, and that is why we keep higher TM. The major consideration in twist selection is meeting the desired yarn and fabric properties. That becomes the most important consideration for twist selection. Do we need because generally we need know that lower twist level leads to increased production, increased bulk and hairiness, and reduced twist liveliness. So, these are the advantages we can say to keep low level of twist, and high level of twist on the contrary will lead to increased yarn strength. It will improve spinning stability, reduces the bulk of the yarn will look now little thinner because diameter will go down. It will reduce pilling propensity and it can improve yarn elongation also. So, advantage is also stated here, and depending upon that we should choose the twist. Low twist and high rotor speed maximize the production, but also we have to keep in mind that how low we should go. If we go for high twist, how high we should go. That will all depend upon the kind of product we want to make from that particular yarn. For same delivery rate, low twist and slightly lesser rotor speed should be preferred over slightly higher twist and high rotor speed. If we have an option between these two for the same delivery rate, there are two possible options: low twist and slightly lesser rotor speed, or higher twist and higher rotor speed. The preference should be given to the low twist and slightly lesser rotor speed, because this will reduce power consumption, because the rotor speed is low.